So another important thing that we have to think about is potential energy. So potential energy is a scalar quantity, again, because it's energy associated with the position of objects within a system. So it has a pretty similar equation, if not like identical, just with a negative sign, with the kinetic energy one. And that's because whenever there is a increase in potential energy, there is a decrease in kinetic energy and vice versa. So there's different types of potential energy. So spring potential energy, if I stretch out a spring, you would have a lot of potential energy, but you wouldn't have any kinetic energy because it's stretched out and it's not moving. If you release it, however, the kinetic energy is going to slowly increase because the velocity is going to get faster, and there would be lesser and lesser potential energy. And then the potential energy would eventually increase because spring force reasons, but I'm not going to explain all that because it's in the different unit of oscillations. So gravity is also similar. In a way, gravity is kind of like a giant spring because it's also a force that's trying to bring something back in their original position. This is probably the thing you're gonna use the most for gravitational energy. So mass multiplied by gravitational Earth constant multiplied by the change in height. That's kind of important because the fun thing about potential energy is that it doesn't really matter where you get it. If you just have a distance between the initial and final, you would have the change in potential energy and therefore work done by kinetic energy, I guess, because the potential energy is decreasing. I tried to make a diagram for this. So basically what this says is kinetic energy is the energy caused by motion, like kinetic stuff, and then potential energy is caused by relationships between two objects. So I thought gravity between two things. That's why I put it like that. And then work is what adds and subtracts energy within a system. So that's why I have arrows going in and out of the system, which is like the square. Don't take this one too seriously because it's pretty poorly drawn. The truly important thing is the mechanical energy. So mechanical energy is kinetic energy plus potential energy plus whatever non-conservative force that was brought upon to you. Any work done in and out of the system is change in mechanical energy. So within a system, mechanical energy is supposed to be conserved. If there's a change in mechanical energy, there probably is a non-conservative force. So that's one good way to know whether or not there's friction or not. And the last thing is power. Power is basically the change in energy over change in time. It's like acceleration in a way. The change in energy being work, you can also get work over change in time, therefore you would still get power. That's just different definitions of power. Yeah, so there's another example diagram, not an example. So within a system, conservative forces can change between kinetic energy and potential energy, but non-conservative forces may take in and out energy of the system. And that was Unit 3. These are the different equations you will use. So that's it. That's Unit 3. Have fun.